So yeah, this is day 9 and these are the topics that we have to cover today. So as you can see on the screen, the first topic that we're going to discuss, the StackUp implementation on the StackUp manager provided by the LTM designer. That we will do first, and in the last session we have discussed several StackUps for 4 layer, 6 layer, 8 layer and 12 layer board. So we know that we are going for the 12 layer, so we'll implement that from different vendors that we have selected. The second thing that we're going to discuss, so again we're going to export the DXF. So DXF is nothing but a outline of a board that is basically provided by the vendors. Okay, so we will export that, and from that we will create the board shape. After that we will discuss the type of vias and their definitions for our requirement, because we're going to use 3 number of internal layers and there will be top and bottom layers as well. So there will be several vias which will be going from outer layers to inner layer and between the inner layers, right? So we will discuss that as well. Next topic that we will discuss, okay, so till now we have compiled the whole schematic. So what is the next step? If we have assigned every footprint properly, that we can check through footprint manager. After that we'll simply import those components on the PCB file. Then the next step will be so after that we'll do the placement planning. Okay, so again, what is the meaning of placement planning? So we know that we have several blocks on our schematic, right? For example, we have LPDDR4 block, we have processor block. Apart from that, we have eMMC, we have Wi-Fi module, we have PMICs, a lot of regulators, right? So we have like 6 or 7 number of blocks, and we will plan where we should place those blocks. So we'll get enough space for high-speed routing. The whole power will be equally distributed throughout the board, right? So a part of board will be, there should not be a concentrated power. Power should be equally distributed. So our board will be, it can tackle the heating problem like that. So that we will do. Apart from that, the 6th topic, okay, so here we will, start the component placement. But before that, before starting the component placement, I just want to assign few colors to the power pins. Okay, so by that we can able to identify where we have to which part of the RK3399, because it has 828 number of pins, right? So which part of that we have to target first, and then we'll start placing these things, which is bypass capacitors, reference resistors, pull-ups and pull-downs, some ferrite beads, few diodes, etc. Okay, whatever the active and passive component which should be closer to the pads of RK3399, that we will do. Okay, so today's assignment will be, which is the assignment number 6. So I will just demonstrate using the Excel sheet that I have prepared for the impedances of all the high-speed tracks. Using that, the task will be, you have to assign the differential pair classes as well as the net classes to the differential and single-ended tracks. Okay, so I will demonstrate one, and using that table from your side, I want you have to assign all of them. Okay, so these are the things that we have to cover today, and will not complete the placement today because it is not possible to complete everything in two hours. So we'll do few part today and the rest in the next session. So we can start with the StackUp implementation. So let's open the PCB first, and this is our just plain PCB that we have created from the project file. Now just open the Layer Stackup. So for that you have to go to the design and Layer Stack Manager. Okay, so this is our default view of a Layer Stack Manager. It has by default 2 number of layers, right? And if you remember, in the last session we have discussed, we have these 3 options. Okay, and out of these 3 we have this one which has all the information given. Okay, then we will create the stack up and we'll just copy or take the screenshot of the stack up that we have created, and we'll share that with the manufacturer and ask for is it manufacturable or not, or is there any modification needed from your end. So then we will do that modification like that. Okay, so things work like that. So we'll just split the screen and start implementing that. Let's close this one, this is not required, and just drag it here. Okay, so firstly we have to select the stack symmetry. So what will happen whenever I will add a layer or a plane on the stack up, it will just multiply it by 2, right? So we don't need to add 12 layers separately. Okay, then later what we will do, we'll remove the symmetry and assign the planes and grounds that we have planned. Okay, so what are the things that we are following for assigning the types of layers? So if you remember, we have already discussed that. So in the design guidelines, if you'll see, they've already given the layer stack up for 8 layer, right? So this 8 layer is like that: top layer, ground plane, power plane, ground plane, then signal and ground plane, then bottom layer, right? In our case, so here we have to add 4 more layers. Okay, so on those 4 layers we're going to add 2 signals and 2 ground plane and 2 signal layers. So how we'll add those? After this signal we will add another signal, then another ground, then another signal, then another ground, then bottom layer, like that. So we'll just going to add this pair here. Hold on. Okay, so okay, perfect. I'm connected, right? Can anyone confirm that? I just got the warning. So Sai, can you confirm that? Am I connected? Okay, I think I'm connected, so we can continue now. So let's open the stack up and just start adding the layers as per this one. So we're going to add 12 layers. So how we can add? We'll just right click here, insert layer above or below. So we can just start from adding layers below and just add signal. So when we add one signal, it will just just maintain the symmetry and add another signal as well. Okay, so this is 4 layer. We'll add another signals. This is 6. Add another. This will be 8. Then this will be 10. And this will be 12 layer. Okay. Now we're going to remove the symmetry here. Otherwise, whenever we do some changes on this one, it will be again maintain the symmetry, and that changes will be undo. So what we will do now? Firstly, we have to see here what will be the number of layers. So for that, we'll just follow this stack up that is recommended by the manufacturers. Okay, so this is the top layer. We'll just leave it at it is. Okay, next will be the ground plane. So for that, we'll do rename that with ground dash 1. Okay, because this is the first ground plane. After that, we have power plane. So this will be PWR, first power plane. Because you can't rename things with the same name, so that's why I would recommend to use these numbering. Apart from that, we'll have another power plane, which is power 2. Then we have another ground, so this will be ground dash 2, second ground plane. After that second ground, we have our first layer of signal, which will be L1. Then we'll have ground plane, which is ground 3. Next will be the layer 2. So these are the internal layers. Then we'll have ground 4. Next layer will be layer 3. And this will be ground 5. And this is our bottom layer. Now the next step is, so these are all the signals here by default. Okay, so we have to change the type, and whatever the planes, we have to just tell the StackUp, okay, this ground is not a signal layer, it is a plane. So for that, what you have to do, you have to just click here and you'll get two options, signal and plane. So just left click over plane, and this is also plane. Similarly, this is also plane. Same here. This is a signal layer. Now we have another ground plane. Just do that for all the planes. Okay. So till here we have assigned the types of either it is signal layer or plane. Okay. Now the next step is we have to follow the StackUp. So let's open the image again. And on StackUp, you can see one is core, another one is prepeg. Okay. So we have to assign that as well. Which one is prepeg, which one is core. So for this, what you have to do, you have to just click here and you will get again two options. Okay. So for the first dielectric that we are using between the first layer and second layer, that is our prepeg. Another one is core, then again prepeg. After that, we have another core, then prepeg. So it is kind of alternate, right? That's it. Okay. Now we have to change the types of prepeg. Okay, which type of prepeg we are going to use. Okay, so here you can see we have to use 2116. Okay, so if you click over this one, so Altium has its own library, okay, which is integrated when you install the software. So if you click here in the dielectric, you'll get these many libraries of material properties, and out of these you have to select the 2116. So you have to just scroll down, and here you will get two options. Okay, this is the prepeg 016 and 017. Okay, and which has few difference in its properties. What is the difference? Their thickness is different. Another changes are their resin concentration is different. So one has like 57%, another is 53%. Apart from that, you'll see the slight change on the dielectric constant as well. So for 2116, which has 53% resin, its dielectric constant is 4.4, and when we increase the resin, the dielectric constant is reduced. So if you remember, it's again a basic formula of a capacitance, because here we have to think about the coupling, right? And the coupling between the layers should be tight. So for that, what will be the capacitance? Capacitance should be higher, right? Coupling means coupling tight, like when there will be tight coupling between the layers, that means the impedance is low, right? And the capacitance is high. So for that, for higher capacitance, and the capacitance is directly proportional to dielectric constant, right? So when you increase the dielectric constant value, the capacitance will increase. So we're going to prefer this one. Okay, let's select that, and we're going to use the same for all the prepeg, which is pp -016. Okay, so let's select for all of these. This is core. Here we're going to select the same, this one. Okay, similarly here. So if you don't want to select like you have to add something which is not in the library, right? So for that, what you have to do, you have to just Altium has everything exposed here, so you can put all the properties of the material manually. So you can edit anything here, right? So you can do manually as well. That we're going to do for core, because here for core they didn't mention like some some standard. So they've just given the thickness of core, and which including the copper, which is this one, right? So including copper, the total width is 210 micro mm. Okay, so let's select all the prepeg first. So here we have these two we have selected. Now here we have to select one more. I hope you're getting my point. Now we have to select another one. Yeah.
So I'm just wondering, can you talk about how I know we're following the stack up for the manufacturer, right?
Mm-hmm.
But in a general case, when do we have to choose between prepreg and core, and the order of the prepreg and core? Can you talk about that after this?
Yeah, sure. See, so order of the prepeg and core is what? As you can see, so when we go for, let's suppose we are going for two number of layers. Okay. So there will be top layer, core and bottom layer. Okay. Then, manufacturer don't support three number of layers. Okay. Because there will be like no space for putting the core. Okay. So similarly here, the again the prepeg is a kind of, so they manufacture number of layers in a pair. Okay, and then using core they basically laminate all the layers. You're getting my point? So in this case, if we are using we are discussing 12 number of layers, so they'll prepare 6 set of pairs. Okay, and then using core, then they'll able to sandwich all those together. You're getting my point? So that's how material property changed, because when they have to add multiple layers together, they have to use different material. Okay, because for two layer they have to just place the prepeg coppers, and they have to just heat it at particular temperature, and it will be connected. Another thing is, if you think from the layers point of view, right? For example, the stack up, if we'll open that. Okay, so if we'll see from the, so again the thickness between the cores is high. Okay, for example, between the power 2 and ground there is a core, right? And its width is higher than the prepeg, right? Because of its material property and the requirement of manufacturing. So we will see, because of this, when the distance will increase, the capacitance will decrease, right? And the coupling will decrease. So because of this lesser coupling as compared to this one, power and power, is it impacting the performance of the PCB? Or whatever the number of, whatever the type of layer we are using, is it impacting that? Okay, so if that will be favorable, then we can go for like either prepeg or core, anything. You're getting my point? Otherwise, we will assign the layer as per the wherever we needed, less gap between those. Let's suppose for this one. So for top and bottom, you'll see here we have prepeg, right? And we know that prepeg is it is way thinner than the core. You can see the thickness here, right? It is 30, it is 365, right? So sorry, 75 and 365. So you can see the coupling between the layer 1 and layer 2 is way higher than the layer 2 and layer 3. Okay, so I hope you got my point, and the order is always same. Okay, when they have to sandwich multiple layers, this prepeg and core order will be same. You will not see all the cores between each and every layer. You're getting my point? But again, if you have a special requirement and you want the greater thickness between those, for example, let's take RF. So again, for RF, what we do, we basically try to avoid ground with the radio frequency antenna connections or antenna routing, like that. We try to avoid ground there, right? So in that case, we'll try to remove copper underneath that, or we just want the maximum space between those track and the copper, right? So I hope you're getting my point here, and this is how you can able to decide. But generally, the prepeg and core order will be like this. It is alternate. Okay, if you not ask the manufacturer specifically like this, some special order you want, this will be the by default order, right? Anyways, so we'll move forward with the selection of prepeg, and we'll just complete that quickly. You got my point, right?
Yeah, I got it. Actually, just one more question.
Yep.
So going back to the stack up in the other picture you had, right? It showed that the distance between the power and ground, in terms of core, right? Core is 365. So why do we want such low capacitance between the power and ground?
Yeah, see, I guess I've already discussed that in last session. So why we want the coupling between power and ground? Okay, so if you remember, I've drawn something on the paint, and it was the 4-layer stack up. And when we change the layer, let's suppose we have a 4-layer stack up, top layer, which is the signal, then we have ground, then we have power, and then we have another signal. Okay, now we have to switch between the top layer to bottom layer through a via. Okay, then how its return path will travel? Its return path will travel from, I can draw that again, because so you can visualize that. Okay, so let's do it quickly. This is layer 1, 2, 2, 3 and 4. Okay, and our signal is traveling from here to here. Okay, this is our signal, and this is via. Now how return path will, so this is ground and this is power. Okay, now how return path will, so whenever the signal start traveling, its the return path will start coupling to the ground. Okay, it will just start returning the current, okay, because of coupling. Now when we change the layer, now for this one, how this return path will go to the ground, it will go to the layer 2 first, which is the power, sorry, layer 3 first, and from that layer 3 it will couple to the ground. Okay, so in case, let's suppose the coupling between ground and power is really bad. For example, we have like very huge gap between, like greater than 4 inch, or very huge gap between the ground and power. So this coupling will be weak, right? And the return path will not, the return current will not get the low impedance path here, right? So it will just spread around the PCB and try to search for low impedance path, right? So in that case, what will happen? Another thing is the return path, which is it will see the high impedance, and because of that high impedance there will be the problem of ringing problem, or it can be interfering with the other tracks, right? Because it will start radiating for the searching of the shorter impedance path. So to avoid that, we always maintain the highest coupling as possible between the ground and power. Okay, so for that, I've already told you the another solution is the capacitor stitching. So for that, what we do, we just add multiple capacitors between the power and ground, like 10 and 20 number of capacitors between the power and ground, right? And through that, we are kind of providing the alternate coupling or alternate path for the return current. Okay, so this is the reason we always go for the better coupling. Okay, I hope you got it.
Thank you. Yeah, thank you.
Okay, let's select this one again. Okay, so till here we have just configured all the prepeg. For core, we don't know any standard here, so we're just going to put it manually. So for that, what we have to do? Okay, so here we have all the information in mils. Okay, so we'll just quickly open the converter here. And let's see if we can convert it to micrometers. Okay, it's micrometer. Okay, anyways, let's go for mm. Split the screen. Okay, so for top layer, the properties are as per the stack up. So again, all the layers are, the top layer is 18 micro mm. Okay, so what is 18 micro mm? It will be 0.018, which is around 0.59 mil. Okay, we'll just put that information here. Sorry. Okay, now we'll see what is the, okay, so this is already defined here. Okay, now we'll see, hold on. Okay, here this information is for the copper. Okay, so go back to the stack up, and this 0.59 is for copper. Okay, for this information we'll use the another stackup that we have for reference. That's why I always recommend just ask multiple manufacturers. Let's see what other information we have. So let's put the information for all the coppers first. So the another copper layer is 35 micro mm. Okay, so for 35 it is 1.37. Okay, so it's already there, you can see that. Now we'll check for the another copper layer, which is again 35. All the internal layers here are 35s, and the last one is also 35. So we'll see. Okay, so this is also 1.37. That's it. Okay, so we have till now what we did, we just changed the properties of prepeg, and prepeg is defined, all the copper layers are defined. Now we'll go for the core. So for core, they are saying it has 210 micro mm including coppers. Okay, so that means they are saying whatever the coppers are here, like this one and this one, this is included on the 210. Okay, so for that what we have to do, we have to just do just little calculation. So we'll just remove 70 from the 210. So what will be, it will be around 160, right? Sorry, 140 micro mm. So let's change that into micro mm. So it is 140, so 0.14, and it is around 5.51. Okay, let's put that information on the core section. So for the core it is 5.5, right? Let's check one more time. Yeah, it is 5.51. Okay, so all the cores, another core is this one, and this is also 5.51. Similarly this one, and same here. And this as well. Okay, so till here what we did, we have defined all the copper layers, all the dielectrics, and all the cores. Now we have to put the information for top overlay and top solder mask. So for that we'll just look into the another stackup that we have from the manufacturers, and you can take anyone. Let's take this one, and if I zoom in here, they've given the properties of what will be the properties of solder mask. So they are saying solder mask is 12.7 micro. So let's convert that as well. So it will be 0.0127, and which is around 0.5. So let's add that information as well, and same here. Okay, now apart from that we have to just tally the dielectric constant for everything as per the stackup. So let's do that as well. So here I guess they didn't mention this one. Let's open the another table that can configure that. Okay, so here the dielectric constant that we can follow is given here. So for the top which is given 3.5, let's change it to 3.3. Another is 4.3. Another is again 4.3. Okay, so these all the internal cores and prepeg have the same dielectric of 4.3. Let's change that quickly. Just let me know if I'm missing something. and the last one is 3.3. Okay, so till here, so again, we are not following the, see, we are taking information from multiple stackups for the 12-layer board, and that will be the combination of all the information, because you have to ask the same manufacturer again. So this is the right way to do that, or alternate way you can say. So in case of any missing information on a particular stackup, like if you want, okay, I have to follow only manufacturer, then you have to just mail them again and ask for other information. It takes like huge amount of time. So until the stackup is not defined, you can't go for the routing, because that will change the thickness of the track, right? When we try to route the differential tracks, if the thickness of the or the gap between the layers will increase, the signal and the return path, the track thickness and the gap between those will also increase or decrease, right? So that means your routing will, you can't finalize the routing until the stackup is not finalized. So this is one thing. We're going to save that file quickly. Okay, so till here we have defined the stackup.